When we want to draw a straight line on a computer screen, we have a picture made of tiny squares called pixels. Imagine you are walking from one corner of a checkerboard to another. You cannot step on a fraction of a square, you must choose whole squares to step on. Incremental line rasterization is the idea of deciding one step at a time which next pixel should be colored, so that the chain of colored squares looks as close as possible to the real straight line. It is necessary because the screen can only show whole pixels without a systematic way to pick them. The line would be jagged misparts, or be uneven, just like trying to draw a line with a ruler on graph paper, without counting the squares in between. The Digital Differential Analyzer (DDA) algorithm starts from the first endpoint of the line and moves toward the second endpoint in tiny equal steps. First, we compute the differences in x and y. Delta x equals x sub 2 minus x sub 1, and delta y equals y sub 2 minus y sub 1. The larger of absolute delta x or absolute delta y tells us how many steps we need. Let's call it steps. Then we compute the increment for each step. X inc equals delta x divided by steps, and y inc equals delta y divided by steps. Starting at x sub 1, y sub 1, we repeatedly add x inc to the current x and y inc to the current y, rounding the result to the nearest integer pixel each time until we have taken steps. This produces a smooth chain of pixels that follows the line. The procedure is: Step 1, calculate delta x and delta y. Step 2, steps equals the maximum of absolute delta x and absolute delta y. Step 3, x inc equals delta x divided by steps, y inc equals delta y divided by steps. Step 4, set x, y equal to x sub 1, y sub 1. Step 5, for I equals 0 to steps, plot the rounded x and rounded y. Then increment x by x inc and y by y inc. Let us draw a line from open parenthesis 2, 3 close parenthesis, to open parenthesis 9, 7 close parenthesis. Delta x equals 7, delta y equals 4, so steps equals the maximum of 7 and 4 equals 7. X inc equals 7 divided by 7 equals 1. Y inc equals 4 divided by 7, approximately 0.571. Starting at open parenthesis 2, 3 close parenthesis. Step 0, plot open parenthesis 2, 3 close parenthesis. Step 1, x equals 3, y approximately 3.571, round to open parenthesis 3, 4 close parenthesis. Step 2, x equals 4, y approximately 4.142, round to open parenthesis 4, 4 close parenthesis. Step 3, x equals 5, y approximately 4.714, round to open parenthesis 5, 5 close parenthesis. Step 4, x equals 6, y approximately 5.285, round to open parenthesis 6, 5 close parenthesis. Step 5, x equals 7, y approximately 5.857, round to open parenthesis 7, 6 close parenthesis. Step 6, x equals 8, y approximately 6.428, round to open parenthesis 8, 6 close parenthesis. Step 7, x equals 9, y approximately 7.0, round to open parenthesis 9, 7 close parenthesis. Notice that the y value we accumulate, the error from the exact line, grows a little each step because 0.571 is not an integer. When the fractional part becomes larger than 0.5, we round up, which adds the extra pixel in the y direction. This rounding error is why sometimes the line looks a little thicker on one side. The DDA carries a small floating point error that is corrected by rounding each step. The error after each step can be expressed as error equals current y minus exact y. It starts at 0 and after each step becomes error plus y inc. When error is greater than or equal to 0.5, we increment the plotted y and subtract 1 from error, mimicking the rounding process. Bresenham's algorithm removes the need for floating point math by using a decision variable that tells us whether the next pixel should stay on the current row or move up one row. For a line with slope 0 less than or equal to m less than or equal to 1, delta x greater than or equal to delta y greater than or equal to 0, we start with the two endpoints and define the implicit line equation. F of x, y equals delta y times x minus delta x times y plus c equals 0. The sign of f tells us which side of the true line a pixel lies on. The decision variable d is initialized using the value of f at the midpoint between the two candidate pixels. D sub 0 equals 2 times delta y minus delta x. At each step we add either 2 times delta y if we stay straight, or 2 times open parentheses delta y minus delta x close parentheses if we step diagonally to d. If d is negative, we keep the same y, the pixel is below the line. If d is non-negative, we increase y, the pixel is above or on the line, and also adjust d. This integer-only update makes the algorithm fast and exact. Here is a clean integer-only version for the first octant, 0 less than or equal to slope less than or equal to 1. Function Bresenham line open parenthesis x0, y0, x1, y1 close parenthesis colon newline dx equals x1 minus x0 newline die equals y1 minus y0 newline d equals 2 times die minus dx. Initial decision variable newline y equals y0 newline for x from x0 to x1 colon newline plot open parenthesis x, y close parenthesis newline if d greater than 0 colon newline y equals 1. 1. Move up newline d equals d minus 2 times dx correction for diagonal step newline end. If newline d equals d plus 2 times die, always add this right step newline end for newline end function. All operations are integer additions and subtractions. No division or floating point numbers appear. The same idea with suitable sign changes works for every other octant. Both algorithms must work for any direction the line can point. The screen is divided into 8 octants. Think of a compass N, NE, ESC, S, SW, W, and W. For slopes between 0 and 1, we step in X and decide when to step in Y. For slopes larger than 1, we swap the roles of X and Y. We step in Y and decide when to step in X. Negative slopes are handled by mirroring the coordinates. If delta X is negative, we draw from right to left, or we can simply take absolute values and later reflect the plotted points. In practice, we write a small helper that examines the sign of delta X and delta Y, possibly swaps them, and then calls the core routine. This way, the same integer logic works for all 8 directions, without rewriting the math each time. Performance: DDA uses floating point additions and a rounding operation each step, which on modern CPUs is still fast but slower than pure integer work. Bresenham uses only integer adds, compares, and shifts, making it typically 2 to 3 times faster, especially on low-power hardware or embedded systems. Accuracy: DDA can accumulate tiny rounding errors, which may cause a pixel to be misplaced after many steps, while Bresenham stays exactly on the grid, because the decision variable is always an integer representation of the true error. Edge cases: when delta X equals 0, a vertical line DDA would divide by 0. We handle it separately by stepping only in YB. Bresenham also needs a special case for vertical lines, but the integer formulation naturally reduces to stepping only in Y when dx equals 0. Both algorithms correctly draw single pixel wide lines, but Bresenham gives a cleaner staircase-free appearance. In modern rendering pipelines, line drawing is often done by the GPU's rasterizer. The GPU receives vertex positions, the line endpoints in normalized device coordinates, converts them to screen space, and then internally uses a variant of Bresenham's algorithm or even hardware-accelerated line drawing units to decide which fragments, pixel candidates, should be generated. Before rasterization, lines may be transformed by the model view projection matrix, clipped to the view frustum, and subjected to viewport scaling. The output of the line rasterizer is a stream of fragment identifiers that go through the usual fragment shader pipeline: shading, depth test, blending. Hence, understanding Bresenham helps to see why the GPU can draw crisp lines efficiently, and why special pipelines exist for wide or anti-aliased lines that bypass the simple integer routine. To make lines look smoother, we can add anti-aliasing. One simple method is to compute the distance of the pixel center from the ideal line and set the pixel's opacity proportional to that distance. The farther away, the more transparent. This is known as supersampling, or the Wu algorithm, which extends Bresenham by calculating a coverage value instead of a hard on-off decision. For variable width lines, we draw a filled rectangle or a thin polygon that follows the line direction, or we offset the basic 1-pixel line on both sides and fill the area between them. Modern GPUs achieve this with geometry shaders or dedicated line width state, But at the algorithmic level, you can think of drawing multiple parallel Bresenham lines and blending their pixels to obtain a thick, smooth stroke.